going to work with all of them, with Radu and Luke, and also with our friend and collaborator Valeriy Slastikov, who's talking here since last year, and I'll be with us today. So this is about the same model that Adriano presented earlier on. Namely, we are considering this energy functional on a two-dimensional unit disk of radius r, sorry. And then the energy is just as simple as imagine sometimes. So this is gradient of q squared. So q is a function from in H1, yeah, defined on this two-dimensional domain, which goes into S0, which is just as the space of 3 by 3 symmetric and traceless matrices, the Q tensor. And then in here you have gradient of Q squared, which is that's gradient squared for each component Qij, where I and j goes from 1 up to 3, and summation over all components. And you have the part which is more specific, this bulk term, which is just polynomial in Q that respects the physical invariances, namely f bulk f of Q is equal to f of r through r transpose, and then one can show that it has to be a function of trace of Q squared, which is this thing here, and trace of Q to the third. So this is kind of the lowest order polynomial that gives you something interesting, and by something interesting, I'll mean that the minimum of this polynomial will be something interesting. Actually, the lowest value for this will be in general something negative f mean. So if I subtract this f mean, I just make this bulk part non-negative. And that won't affect the minimizers, right? I'm just subtracting a constant from here, but it's convenient to have this non-negative, yeah? And the fact that the minimizers belong to a non-trivial set is contained in this statement here, that the limit manifold or the vacuum manifold, yeah, the set on which this polynomial attains its minimum is it can be written in this special form. A constant here can be explicitly computed in terms of these coefficients A, B, and C, and a matrix, a 3 by 3 matrix that has a very special form, namely it's of the form V tensor B minus 1/3 of the identity. V is a unit vector, yeah, and in here, V tensor V is just Vi, Vj, where V goes, V is V1, V2, V3. Okay. So here, if I replace V with minus V, I get the same thing, the same matrix. So this set of matrices, yeah, is really just a way of writing RP2 in terms of matrices, or otherwise said, it's homomorphic with RP2, which is RP2 is the set of lines passing through the origin. Okay, so this is what Adriano mentioned before, and now what we are interested in are two-dimensional point defects. So we look at what happens on 2D. I mean, in principle, you could also have you could imagine you have a 3D domain in which you don't have dependence in the z direction, and then that's how you reduce to the 2D case. And we'll look at well, there are of course a lot of works in the well, in the mathematical literature on crystal. So here are some of the names. Some of which are also present here. So we'll be looking at what is called strong anchoring. So that means fixed boundary conditions, yeah, of this form. So the boundary conditions are taken to be in the set of in the minimum set for that bulk curve, and we will take n to be of a very special form. Namely, if you write it in polar coordinates, so you have the boundary r cosine phi and r sine phi, where phi the angle, the polar angle between 0 and 2 pi. We'll take the boundary conditions to be of this special form: cosine of k to phi, sine of k to phi. Yeah, and if k is equal to 2, then that's cosine of phi, sine of phi. Very nice. It's just radial. Yeah, something as in here. Yeah, it's getting more interesting when you have k is odd, because, for instance, if k is 1, yeah, you start with something like this, which is 1 and 0, and then you rotate it, and after 2 pi, you'll get something with opposite sign, cosine of pi, sine of 0. Yeah. So for k odd, you get something discontinuous. Yeah. If you were to use this n, but if you use n tensor n, where yeah, don't distinguish between n and minus n. Yeah. So you have a topological difference between k even and k odd, and this can be seen in these pictures, which are standard pictures of what is called index, say 1, -1, 2, and -2 defect. Yeah, and okay, this is one point that Radu mentioned before. This is related to the degree, with the topological degree, and there is this mismatch here between the mathematical terminology, where the degree is an integer between that characterizes maps between manifolds of the same dimension, and the index, which in our case can be half integer. Yeah. So how do you count these indices? That tells you really how many times it's like also called winding numbers. It tells you if you, I mean, you have a defect here, right? So these are points where you have discontinuity in these line fields, right? And then you look at what happens on a circle around such a point defect, and you look at how many times the lines rotate as you go along the circle. Yeah, and then here you'll see that there is like one rotation, one full rotation. Okay, and this is the kind of picture that provides you a topological perspective of what happens. Yeah, if you were to use just these kind of objects, right? So line fields or vector fields. Yeah, if you are into this fortunate case where k is even, you can put arrows and turns the line fields into vector fields without creating additional defects. Yeah, in here you wouldn't be able to put arrows, because if you try to put arrows here as you go along, you'll see that you have to come back in the other direction, right? So this is sort of a more constrained, more geometrical picture. Yeah. In general, when you have more constraints on the target, as Adriano put it before, namely by using this Ljuksitov constraint, that gives you a more rigid situation, more geometrical. So you have hopes to do a qualitative analysis. Yeah. However, you are losing something. You get or get defects. Yeah, you get these things that have infinite energy. The physicists don't like infinite energy. So you can get rid of this infinite energy using really these Q tensors, using the fact that you don't need to restrict yourselves to these special type of matrices. You really have more freedom in using more general matrices, right? you could use these 3 by 3 symmetric and traceless matrices in their full glory. And instead of having these pictures, you have a relaxed version of these pictures, namely you have these things. Yeah. So in here you can draw these Q tensors as parallelepipeds. Yeah. And the relationship between the parallelepipeds and the Q tensors is that you identify the axes of the parallelepipeds with the eigenvectors of Q tensor, and the length of such a parallelepiped to be proportional with the eigenvectors of Q tensors. Yeah. So the eigenvectors really they add up to 1. So you really need to add a constant to all of these eigenvectors to make them positive. But morally, this is, I mean, in many ways, this is a relaxation of the previous pictures, and you can get from something like this to, so this is index 1 half defect. If you were just to squeeze all these parallelepipeds into one line corresponding to the largest direction, yeah, you'd get this, oh, sorry, this thing here. Yeah. So these additional degrees of freedom that that are provided by the higher dimensionality of the Q tensor allow you to avoid this singularity that would appear here in the center, just because here, instead of having something becoming singular because it's different from different directions, this will turn into a different object. It will come to be just sort of one or one parallelepiped. Yeah, that will be something like this. It's not wrong here. But the point is that these additional degrees of freedom allow you to escape this singularity, but there is usually a price to pay, in which is that you have multiple solutions, right? So it's harder to do qualitative analysis to understand what are the features of the qualitative features. Okay, and okay, the system is quite interesting looking, right? I mean, it's just a semi-linear system of elliptic equations with this polynomial right-hand side. I mean, it's really, in here you have 9 equations, but only 5 of them are independent. And you have Q on the boundary to be of that special form as plus n tensor n minus 1/3 of the identity, right? And the goal is, and again, this is on the 2-dimensional domain, and the goal is to understand how the minimizers look like. Yeah, you have this symmetry of the boundary conditions, but usually there is some sort of symmetry loss from the symmetry that you have at the boundary to the symmetry that the solution exhibits. Yeah, and we will focus mainly on the case when k is even, and I'll explain you in a moment the difference that is important for us. And again, if you, as I just mentioned, k even is in some sense topologically simpler, yeah, than the case when k is odd. Okay, so we will be looking at these special solutions that still exhibit some sort of symmetry. Not as much symmetry in some sense as you have in the boundary data, but some symmetry. And then we have this notion of symmetry, which is k-fold SO2 symmetric. And there is this scary looking definition, which tries to say really something like this. So if you have, I mean, you are interested in what happens along the radii, yeah? And to understand what happens when you change the radial direction, say, yeah. So if you have an object which makes an angle like this, and you move it around, you move the radius, the object will try to move in a similar manner so that to keep the angle, essentially, yeah. So that means that you are interested in what happens when you change this x, yeah, x is x1, x2, and then you have a bit of a problem here because x is in two-dimensional and then Q is like a 3x3 matrix, right? So that forces you to put this sort of rotation. I mean, this is really a genuine rotation matrix, which you extended to 3D, yeah, just by putting this additional component. And then you also extend the two-dimensional vector to 3D with this tilde, yeah. And you also can put it back with this projection, yeah. So if you unravel all this, this says that in order to understand what happens at the point x, you see, I mean, what happens at the point x is what happens when you rotate that point x with an angle k over 2 psi, yeah. And I mean, it looks a bit scarier just because of this matrix, yeah.
It's a K, not R2.
Right?
In the middle.
Yeah.
Up.
Yeah.
The index.
Yeah, yeah, the index is a K. You should have a K here. Then.
No.
It's two.
No, it's two. If you do a rotation like this and you see how the angle changes.
The target rotates.
At the end you want to do a full thing.
Okay.
Yeah, so it's when K is 2, it's like I theta.
Yeah, because it's a rotation with just it's a normal rotation in the domain. The normal rotation in the domain. You obtain so it's this x1, x2. You rotate it with psi, yeah. And then you get a three-dimensional thing which you put it back to make it two-dimensional. Yeah. So instead of if you start here with x1, x2, you just rotate it to psi and you get here. Yeah. And then Q is rotated with angle k over 2 psi. Yeah. Okay. So it's a bit more convoluted, but that's the basic idea that I wanted to before with the geometrical rotation. Okay, and then you also have this up and down symmetry, 0-1 symmetry, which is symmetry with respect to this vector. And you have this matrix, yeah. This is a reflection with respect to this vector. And finally, you have this O2 symmetry, which is like a composition of this symmetry and the previously mentioned symmetry. And you have still an up and down symmetry, but in the so this is like a reflection with respect to the other to the E3 vector, yeah. So now the difference between the minuses here in the middle and the minuses here. Yeah. Okay, so you have various types of symmetries relating to essentially different parts of the eigenvectors. Yeah, and the useful, say, and important outcome that these symmetries have is that you will be able to reduce this Q tensor that has such symmetries to a simpler description, yeah, using multiplication. So you use well, I mean, you devise a basis that takes into account what happens on the boundary. So this is something like this, n tensor n, where again n is exactly the boundary data, and you add some other. So this is something that changes when the polar angle phi changes, and then you also have these vectors which are constant. Yeah, and the important thing is that these are orthogonal. They are orthogonal in this Frobenius inner product. yeah, which is a trace of their product. Yeah. If you take trace of E0, trace of E1, that will be 0, and trace of E0 squared will be 1. That's why you choose specifically this normalization here to make sure that the trace of this squared and the trace of this squared is 1. Okay. And the important thing here is that if you use this kind of basis, yeah, this symmetry, Z2 times SO2 symmetry, will amount to the fact that Q of X can be decomposed in this basis into something which depends just on the radial component. Yeah, so in principle, you should have here W0, R, and phi. Yeah. However, because of the symmetry that I mentioned, it can be shown that it depends just on R. And that will be very important because it will allow you to reduce the system for Q, which is a PDE system, to an ODE system for W0 and W1. Okay, so quite a significant reduction. And then you can have this less restrictive symmetry where you have a similar story, but now with 3 components instead of 2 components. Yeah, so the same 2 basis vectors, but now you have this third one, which is regular enough only when you have even components. Yeah. Otherwise, you have a discontinuity here because now you don't have n tensor n, you have just n. And remember that when you rotate this by you have a problem when k is odd. Yeah, so this is in H1, that's when k is even, right? So you have this solution with 3 components. Yeah, and again, W0, W1, and W3 are radial. Yeah, because of this symmetry, right? So what we'll be playing with really is this will be alternating a bit between these 2 cases when you have 2 components or 3 components. Yeah, because these give you different different solutions occasionally. Yeah. Okay. Now, results for k is even. Now, when R is small, there is just one critical, well, there's one critical point, one minimizer really for the problem, even for the PDE, yeah, and that's just because the energy will be convex, and that's due to the Poincare inequality, which allows you to control with a gradient, you control the L2 norm is a very large constant. Yes, so the smaller the R, the larger the constant, and then you can see that the energy is convex, and then you have a unique minimizer, which has to be of this simplest form with 2 components. Yeah, it gets more interesting when you have R large, and that's really the main part of this talk, to show that there are 2 global minimizers, right? When R is large, and these are minimizers with 3 elements. So there is this component which is non-zero. Yeah, and it turns out that this is just a calculation. If you have some W3, you can put minus W3 and you get the same energy, right? So this gives you for free another solution once you have a solution where this is non-zero. Yeah, and there is an analogy with Ginzburg-Landau and the situation when you have 2 versus 3 components. Yeah, And in this case, the important fact that we'll be referring to again and again is that this additional degree of freedom, these additional components that you have here, so you have three elements in describing this minimizer, allow you to destroy some of the topological constraints imposed at the boundary, and your energy will stay essentially bounded as R tends to infinity. Yeah. So again, this is like in Ginzburg-Landau. So what is the story there? This is the Ginzburg-Landau energy in which you are on a 2D domain, and you take values in the yeah. So say you put something like this. So this kind of boundary condition that we were mentioning before, and you put this K to be even so that you don't worry about line fields, and then the critical points, just out of the symmetry argument as before, you see that the critical points are two-dimensional with possibly a third, with an escape into the third direction, right? So, I mean, in principle, these are functions taking values into R3, right? So, but they could also take values into so they could take values without the third component, yeah. And it turns out that if you write this symmetry condition, then they should be of this form, yeah. And now there is the issue of whether this component is active or not. And what can be shown is that you have that this component is not active when you are small, when R is small. Yeah, there is again because of this Poincaré inequality that is also here. This energy is convex, so there is just one minimizer and critical point actually, yeah, which is of this form. Yeah. And if R is large enough, there is a component escaping into the third direction. And the important thing here is that you have degree one boundary conditions. If you were to stay in the plane, then you'd have this logarithmic growth of the energy. Yeah. If you escape into the third dimension, as you have here, you reduce the energy and you have bounded energy as R tends to infinity. Yeah. So this is the simplest manifestation of how you escape the topological constraint imposed by this degree one boundary condition. Yeah. Which would make the energy in the limit when R tends to infinity, energy infinite, yeah, and that topological constraint is escaped by allowing this variation to the third direction, right? And there is this change of variables, if you wish, namely the case when R tends to infinity is the same as putting R equal to 1 and putting a 1 over epsilon squared here, yeah, which is as in here. This is just a change of variable, and then you can think of this problem when you have no constant here, but instead R grows, or you keep this and then you have this penalization here.
Arghir?
Sometimes this is more geometrical. Yes.
A quick question. Go back to the scaling energy there. So what is the prefactor? Is the prefactor dependent on the degree?
It's a constant, but
Universal constant?
Universal depending.
So what I have in mind is basically what I have in mind is the stability, the high winding number whether they decompose into lower order defects.
This is just stable for k is equal to 1. Yeah. You have higher than it's unstable, higher than 1. Okay, so as mentioned, the case when the radius is fixed, you have here a large constant is more illuminating, if you wish, because it tells you what happens when epsilon tends to 0. So when epsilon tends to 0, this thing, which was renormalized to be greater or equal than 0, will try to stay as close as possible to 0. And namely, it will try to stay as close as possible to Q tensors, which have this special form as plus n tensor n, where n is now a function defined on this unit disk with values into S2. Yeah. And the fact that you put k even is what makes a difference, because if you were to put k odd, you'd still get a topological constraint that would be felt still at the level of these functions, components, because you cannot escape into the third direction and still have finite energy. Yeah, well, I mean, you can do this for k even because you have orientable boundary conditions, but you cannot do it for k odd because you have additional constraint of this non-orientability. Yeah. So the difference between k even and k odd in what we're doing here is the fact that in this case that the limit is smooth. Yeah, and that will be quite crucial for all arguments that will present. In principle, you could try to do the same story for k odd, but then the limit will not be smooth, and a lot of the things that we present here, well, the same game would not work directly. Yeah. Okay, and so as epsilon tends to 0, or alternatively, in the other perspective, as R gets large, Q approaches this limit profile, which is smooth, and it's minimizing harmonic map. So just like in Giano's talk, this is a game around harmonic maps, in this case with values into the sphere. Okay, and these minimizers are O2 symmetric in the sense that they can be written in this form with the same basis as the Q before, and you have this W3 component, which is can be computed explicitly, and it's non-zero. Yeah. And then you can try to see what happens also if you have this O2 symmetry. Similar story. Now, what do you really do in order to prove this uniqueness that I was mentioned? So, for small epsilon, as I said, you have smooth limits. So, it means that you'll be able to converge uniformly. Q epsilon would be uniformly close to this smooth limit harmonic map. Yeah, and then you are the images will be in a tubular neighborhood from this smooth Q star, and you decompose this into something which looks like a limit problem with a perturbation. Yeah. So there is this psi, which is really to linearize this Q star that is the limit. And then there is a perturbation which is of order epsilon square. So you write it in this form where P is of order 1. Yeah. And this decomposition is chosen to be not by the obvious thing that is this orthogonal projection onto this limit manifold, but this this transversal projection, which makes sure that this difference between the limit and the Q is in the plane which is in the normal direction to the limit manifold, also at the point Q star. Yeah. And then you write this Q in terms of these new variables that are psi and P, yeah, and then you have equations for psi and equations for P. And you'll be able to show that psi is a function of P. It depends in a Lipschitz manner on P, and then you put this psi of P in here, and you obtain a closed system in P for which you'll be able to use a contraction argument to get a unique solution, right? So. So this is really based a lot on having strong information about the limit solution, yeah. And in closing this this kind of mechanism here, where you want to obtain dependence of psi in terms of P, and then this contraction argument. And this is all set up in strong enough norms, yeah. So that's why at least this argument uses the high regularity of the limit and star, because that will allow you to have good uniform regularity. Uniform is suitable epsilon weight, let's say. And close all the arguments here, right? If you don't have, I mean, if you have K odd, then N star will be very singular because of this point defect, which in principle you can hope to isolate, but it's quite clear exactly how this is the point defect is located, yeah. Unlike for standard, say, orientable defects, as in Gilbert-Landau, the non-orientable defect that you get when K is even, where K is odd, is much less understood. You know, you don't have the same nice asymptotic description of it to isolate it. And yeah, so what I'm trying to say here is that extending this to the K odd is could be non-trivial. Okay, now the thing that I want to emphasize is that all these arguments also allow you to get the existence of 5 critical points, not just 2, as I mentioned before. Because for one thing, you can try to minimize just in the case when you have 2 components, yeah. So you do restricting the minimization. So this is what this QSTR is. So this is the value of the minimizer of the energy functional when you use just 2 components, so you don't allow to escape in the third direction. And in that case, you'll have a logarithmic blow up of the energy. This is what this lemma here tells you, that if you want to use just 2 components, then your energy will blow up logarithmically as R increases. Remember that we were using 3 components, the energy was bounded as R increases. Yeah. So this provides you a critical point in the class of all Q tensors, which is unstable in the class of all Q tensors, yeah, and has high energy, log R, yeah. And you can have these two global minimizers that are different just in the last component. Yeah, and then you can construct a mountain path solution connecting these two global minimizers. And you construct the mountain path solution with an energy which is also bounded when R is large. And then the mountain path solutions will have bounded energy, and then the critical point that you obtain, yeah, will have three components, yeah, and it will have three components which are all non-trivial, yeah, because if the third component were trivial, then it would have large energy. Yeah, that's what I just said before, that if you have two components, then the energy, the minimal energy, has to be logarithmic in R. So if you have a critical point with two components, with three components, then all three have to be non-trivial. Yeah, and if you have a component, third component, which is non-trivial, then you can just change the sign and obtain one more critical point. So this instead of QMP plus, you can change the sign, the W3, and get QMP minus. Yeah. So this way you have really four critical points. So you have these two global minimizers, which are with say W3 plus and W3 minus. You have one connecting them, yeah, with bounded energy. And once you have one such unstable critical point, you have another one where you change W3 by minus W3. And then you have the fifth solution, which was that solution with logarithmically large energy. So these arguments with restricted minimization allow you to obtain this richness of solution. Of course, this is not to say that you don't have more solutions, at least, but if you have a more complicated solution, they should be far away from the limiting harmonic map. Yeah, so they won't be minimizers; they would be just critical points. Yeah. So yeah. That's about it.